This time I will start a beam design. So this is a problem from your book. This problem says there is a simply supported beam, 30 feet span, dead load 2 kip per feet, not including self weight. Live load 2 kip per feet. That means it's a uniformly distributed load. Use rho 0.18 E prime C over Fy. Material properties. The material you will use is 4 KSI concrete, 60 KSI steel. Now some discussion here is that in real life they will not recommend you the row. Typically nobody will recommend you. Your owner, client, they will not recommend you any row. You, as the engineer, you have to decide. But this problem gave us, so we will use it. Okay. Something else to observe, the beam dimension. The beam dimension B and A is not given. Not given. Sometimes architects will provide this. So there might be so many different scenario in field. So there is no unique recipe that you can follow in big design. Sometimes you may know this, architect already told you. Sometimes you may know this because your boss or supervisor may recommend you. Sometimes you do not know this, you do not know this. Now sometimes self weight included, sometimes not. So there are so many different scenario. So do not memorize anything, just know the fundamentals and know how to solve it. Okay, so we will start this beam design. So step number one. Step number one, I am writing a step. It is not any formal step or book language. I just it's my style so that you can follow. Step number one, always solve the self weight problem. If self weight is given, good. Step number one is done. If not given, assume something. Now, how much to assume? Yes, even I do not know this answer. But based on the experience or like common sense, this is a 30 feet long beam. It's a huge beam. Load is also huge. Uh, I suspect that this beam section will be huge. So I will assume say self weight how much? Say 550 pound per feet. I will assume that 550 pound per feet. Okay, let me see your book. Yes, your book did not give us any self weight. So we will use this. Now, so this is number one. Step number two. Once I know self weight, I will do my load calculation. Load calculation. Load calculation and combination. In another video, I discussed what is load combination. As ASCE recommended different combination and different factors. Okay, so you saw that. Okay, load calculation, but load is already given in this problem. We do not need to calculate. Now, so if I include self weight, my dead load will be how much? Dead load will be 2.5 is 0.55, right? 2.55 kip per feet. How? Self weight plus my 2.55, and live load will be 2 kip per feet. That is my service load. Now I have to factor it and load combination. You know that when there are only dead load and live load, the combination number 2, if you can remember from AC, combination 1 is 1.4D, combination 2 is 1.2D, 1.6L, then 0.5 snow load or rain load or roof live load. You saw that kind of combination is 3 up to 7. So when there is only dead load, live load, this one will win. So our uniformly distributed load 1.2D, 1.6L. For reinforced concrete design, mostly beam column, and this combination number 2 will always win. So we will use this. What is WU? U is uniformly. By U we use W to represent uniform load. Why it is U? U means ultimate. Ultimate means already factored. So we use U to represent ultimate. W represent uniformly distributed. Who told it? Nobody. It is a common practice, yes. Over the years, people are using this symbol. So 1.2 dead load is 2.55 kip per feet. 1.62 kip per feet. I am getting how much if I use my calculator? 1.2 times 2.55 plus 1.6 times 2, 6.26. 6.26 kip per feet is my load on this beam. So step number 1, separate to load calculation and combination. So we use second combination. Why? We know that is from our experience. For most dead load and live load, this one will win. This one, snow load, rain load, roof live load, there's no this kind of load in this beam. Okay, so now step number 3. Once you find the load, we have to find the moment. Okay, yes. So step number 3, calculate your moment. So what is your moment? For uniformly distributed load, the moment is calculated WL square over 8. So W is 6.26 kip per feet, L square is 30 feet, and 8. How much? If I use my calculator, 6.26 30 square divided by 8, 70425 kip feet. This is my factored moment, ultimate moment, that means factored moment. Once we find this, we'll go to next step. Step number 4. What is that? Deal with rho. Step number 4, deal with rho. What is that? If rho is given, it is given. No, there is nothing to do. If it is not given, you need to select it. So as it is given, we will use this, but we have to check it. We have to check whether we are using a rho that will give us a ductile section. If you can remember several lectures earlier, I told you in reinforced concrete, the tensile strength should be at least 0.005. In that case, my section will be ductile. In that case, P is 0.9. If you can remember this is phi, this is epsilon T. This is 0.005, 0.00207. Yes, this value. We want this area. This is ductile region. So we should check it. Yes, if my section is here, good. If it is here, I need to calculate my phi. If it is here, we should not use the section. So we should check it. Yes, we'll check it. 0.18. If prime C is 4, and if Y is 60, you can write 4,000, 60,000. Okay, where's my calculator? 4, 16.18. I got 0.012. Now, is it good? Like, is this reinforcement ratio good to maintain the ductility? We should check it from the book. How to check it? In your book, if you go to appendix, there is a table A7. In the appendix, table A7, table A7, I would say that the most important table in your book. Most books have it. So if you use other book, no problem, we will define numbers. Where for define Fy, define F prime C. define F prime C, define Fy. You will find row balanced. You know what is row balanced. Row balanced means my steel will yield and concrete will fail at the same time. But it is a boundary. You should not go there. Row when epsilon T is 0.004. 004 means somewhere here. Many designers say if you cannot maintain 0.005, 004 is also okay. That value. Then a row when epsilon T 0.005. Then row minimum for flexure. This reinforcement must be greater than the minimum for flexure. Okay. So our F prime C is 4, Fy is 60,000. If I see, I marked it because these are the most important value, and these are the most important properties of concrete and reinforcement. So I can see here row when epsilon T 0.005, it is 0.0181. So I would say row at epsilon T is 0.005. How much it is? It is 0.0181. 0.0181. And what is row mean? Row mean is given 0.0033. Yes, so I got this true value. Now, sometimes we call this row max. Sometimes we call this row max. But yes, it is not actually row max. It is our design terminology. Row max, that means whatever will give me this. If we use more than that, our section will come in this side. So this is why sometimes we call row max, but it is actually not row max. Row max should be the balanced, the boundary. Okay, whatever. So minimum is 0.0033, max is 0.0181. Our value in between these two. So good. Okay. Yeah, if we use more than this, our section will come towards this way. Now we are using less than this. So we will be roughly somewhere here. So after 0.005, that means the given is good. Again, if row is not given, you have to select from based on this. I will always select row max. Row at epsilon T 0.005. I select this one. If it is given, check it. If they gave you less than this, no. Tell them that okay, now increase at least this, or even up to this. So the story of row is done. So now our next step is the most important step. Actually, every step is important, but yes, that is something critical. Okay, I need this value. So I will. So this is my moment. This is my row. Okay, next step is step number 5. In this step, you have to decide which way to go. When you know your moment, you know your row, that means your life is very simple. How? In your book, appendix table A8 to A13 table A8 to 13, they give a value. Yes, they give values of EMU phi BD square. They give this value for different F prime C, Fy, and row. If you know this, you can find this value in your book. Now, where we got it? In flexural strength equation. If we expand that equation, if you can remember that there's equation phi BD square rho Fy. Exactly, I forgot the equation. Something 1.7 F prime C rho Fy, something. Yes, similar equation. If I go to your book, I can find that equation. Okay, let me go quickly. Which chapter it is? It is chapter rho b rho p b 1 point. Yes, it is right. Is it a magic? No. For some reason, whatever I wrote, it is right. Okay, so if I bring this portion here, so p b d square. Yes, you can calculate this, but your book already gave you this value. If you know rho, fy, f prime c, your book gave this value. So you can just go and pick. Okay, so if I go to your book, I will not calculate it, I will use your book. Okay, what is this value for this row? So I am going which table? Table A2, A13, anyone, okay? You have to check this, yes? Check this. A prime C and Fy. Table A8, A prime, Fy is 40,000 psi, A prime C 3,000 psi. Table A9, Fy 40,000, A prime C 4,000. That is not. Table A10, Fy 50,000, A prime C 3,000. No. Table A12, 60,000, 3,000. No. A13, 60,000, A prime C 4,000. Yes. Find row 0.0012. 0.0012. 0.0012. Yes, I found it. 0.0012. For that case, mu PBD square 643.5. Okay, let me check again. Yes. So hopefully you got it from table A13. We used A13. Table A13. We got this value. You can see your book. Now, something to discuss, that this value is based on pound and inch unit. Our moment is feet. So be careful, okay? Then we got this value. Now, we know this. We know phi because phi is 0.9. Our reinforcement ratio is less than the max. We do not know BD. We can find BD now. Okay, so BD square will be mu P or 3.5. If I am right or wrong? Right. So what is my mu? 40704 times 24 times 1000 times 12 pound inch. Why 1000 to make it pound? Why 12 to make it inch? This is a critical because this value you got it from the table is based on pound inch unit. So divided by phi is 0.9, 463.5. How much it is? 70425,000 divided by 0.9 divided by, so I will erase somewhere here. We do not need it anymore. So step number 5, still we are in step number 5. So I found BD square is 4592. Yes, 14,000. Yes. Now what to do? So we got BD square 14,592. Now you can play. Yes, if we assume B, what should be your D? Say B is 14. say B is 14. What should be D? If B is 14, then D should be this divided by 14 square root 32. Okay, 32.3. If B is 16, 14,592 divided by 16 square root, it is 13.2. So in this way you can find different ratio. Our main target is H by B ratio. H by B ratio should be within 1.5 to 2. Let me see. Okay, no, it should be good. This should be 1.5 to 2. Okay, what about other combination? If B is 18, 14,592 divided by 18 square root 28. Now get that. Now it is D and H by B ratio. Okay, let me go to the book again. Yes, you need to go to book very often. Yes, actually this is not H to B ratio, this is D to B ratio. So D to B ratio should be 1.5 to 2, not H. That is why I was thinking something wrong. D by B ratio should be 1.5 to 2. Okay, so what is the ratio here? More than 2. What is the ratio here? Less than 2. So it looks this will be a better choice. So 32.3 divided by 14. Here it is. Here my ratio is, for this case. Okay. For this case my ratio is 2.3. For this case my ratio is 1.88. For this case 1.55. Yes, so this is good, also okay, but I will choose this one. Yeah, I'll round up. Okay, so if I take my eraser, so in step number 5 we played with this. There is some discussion here. What is that discussion? If I do not know BD, this is the way. If I know BD, then what to do? If I know BD, then what? Calculate this portion first. Find this value, go to table, find row. So if you know BD, you have to find row. Here, you know row, you found BD, opposite. Now what about if you know BD and if you know row, both? Then you have to check it that BD and that row like match with minimum, maximum, so everything is, that will be, but that is an uncommon case. Typically you do not know both. You know either BD or row or none. If you know none, assume some row, find BD. Whatever we are doing here, except it is given. So we will assume find BD. So here you need to play with whatever given, whatever not given. Okay, so we will use this value. So step number, oh, now this value is not a round number. We'll make it round. Say 16's width. D we will use 30.5 inch. We'll round up. That means this is 16. This portion will be 30.5 inch. Now, you know that there is some clear spacing, clear cover here, some tie here, but this spacing, if we use 2.5, very barely or very tightly, you will meet the requirement of cover of 1.5. So you can use 2.75, 3 inch, but 2.5 is a very conservative, very tight design, but 2.5 is okay. Again, if you use 2.5, you can maintain 1.5 inch cover. Some slightly less. Now this 1.5, is it sharp? No. You can go little here and there. So again, I will assume from center of the bar to here is 2.5. In this way, you will be able to maintain this very tightly. But again, 2.75 is good to be. Yes. Not good, is better. Yes, better. Can we use 3 inch? Yes, then you will have sufficient space to cover it. But 2.5, very tight design. Still though, I will use this because I do not want to waste material here. Okay, it means what? It means my ace will be 30.5 plus 2.5 is 33 inch. So my beam is actually 1633 inch beam. Once you finalize this, I forgot which step number it was, most probably 5, then 6. What is 6? Check self weight. Can you remember at the stage number 1 we assumed self weight 550 pound per feet. Now what is the self weight of this? We have to check it. Okay, so 16 divided by 12 feet, 33 divided by 12 feet. What is the unit weight? 150 pound per cubic feet. Simply the cross-sectional area times the unit weight will give you load per feet. How? Feet cancel, feet square, pound per feet. How much? 1633. I don't know it is a magic or no. It is exactly 550 pound per feet. So okay. Why it is okay? Whatever we assumed at the beginning exactly matches. So it is okay. Now what happened if this value is more than this? Not okay. But you assume 550, you got here 560, 570. Is it a problem? I do not think so. If you assume 550, you got here 450. Is it a problem? No, you are in safe side. But if it is more, I will recommend to go back. Step number 1, increase your self weight, calculate load, everything. Yeah. So design is always trial, loop, yes, loop. But luckily for our case, we are okay. Okay, so step number 6 is done. Step number 7. Step number 7, as it is okay, we will continue. If it was not okay, we will go back and increase my self weight to everything. Self weight is reinforcement. You know that rho is ASBD. So AS is rho BD. What is your rho? 0.12. What is your B? 16. What is your D? 13.5. How much? If I use .86 inch square. So you need to provide this amount of reinforcement. How many bar? You do not know, right? So if I open your book, appendix, table A4, I think. Table of A4. Table A4, it will give you different types of bar. So you need 5.86. So find here So this is number of bar, this is bar number, that means bar size. If I use say 6 number 9 bar, it will give me 6 inch square. Okay. If I use 6 number 9 bar, it will give me 6 inch square reinforcement. I need 5.86, so good. But try to be very close to it, because if you provide so much, your reinforcement ratio will decrease. That is risky. That means if you provide so much here, your row will change, and you have to check your phi value again. Maybe you did not understand. There's something here. So you need 5.86. You are providing 8 inch square. 8 inch square, right? If you provide this, what is the problem? Your row will change. Your row will change. Say 8. It becomes 0.016. So the here is 0.12. So you have to go back using this row, find your A, then C, then beta 1, then epsilon T, then find your phi. So you have to check that if you provide so much. So do not provide so much. Yeah, I am happy with this, but again something to consider. In this 16 inch, you have to accommodate 6 bar. It is tight. You have to check it. Okay, let us check that this is a good design or no. But what are the alternatives? Alternative is here you have to play a lot. If I provide 4 number 11, 6.25, but not a good size, because I should not provide more than this. Actually, there is no other good size. So table, I am solving a, okay, I am using table A4. So we will see. We will see whether it is okay or not. So that is our step number. What is the next step? I forgot the step number. Most probably 7 or 8, yes? Or simply next step, yes? Next step, detailing. So detailing, check whether it is okay. How to check? That means we should check that whether I have sufficient clear space. Let us find clear space. Okay, I am drawing here so that you can see better. Yes. 1, 2, 3, 4, 5, 6, and I will provide a tie. This bar is how many? 6 number 9. So tie bar will be number 3. Why 3? Main bar is less than 10. Do I have clear space here? What is the clear space? Total is 16. I will deduct center to here 2.5 and center to here 2.5. Center of the bar to the edge, if you provide 2.5, you will very tightly meet the requirement of clear cover of 1.5 inch. If you do not, or if you cannot, some less than 1.5 it is okay. It's not tight. So if I deduct to 2.5 from both sides, this is cover, yes, from center of the bar. Again, maybe my drawing is not good. You should make a very good drawing here. No vague drawing, very good drawing. 1, 2, 3, 4, 5, 6. this is your so here to here, here to here, 2.5 inch, 2.5 inch. So 2.5 is cancelled. Then how many bar? 1, 2, 3, 4. 4 bar here. 1, 2, 3, 4. Half here, half here. So 5 bar actually. So 5 bar, diameter of the bar is 9 by 8. Number 9 bar. This is 6 number 9 bar. So die is 9 by 8. So this space will be lost. The remaining space will be divided by 1, 2, 3, 4, 5. Divided by 5 is my clear space between 2 bar. So 16 minus 2, 2.5 minus 5, 9 by 8. 5.375 divided by 5. I got 1.075 inch. Is this clear space good? We know that minimum clear space should be 1 inch or bar diameter. What is my bar diameter? 9 by 8. 9 by 8. So 1.125 inch. So we need this amount of space. This or this, whatever is larger. We need this amount of space. But I have this amount of space. What to do? Actually, it is not okay. But again, it is not that a problem. Yes, very close, very close. So if you say this design is okay, no problem. Just say that or this. The clear space of 1.75 inch is very close. So you are saying okay. If you say it is okay, based on this judgment, your design is not wrong. Yes. This kind of assumption is just empirical by experience. It's not sharp. But again, I will recommend to what I can do. I can bundle these two. I can make this bundle. This 2 bar bundle here. Then there will be huge space. That is an alternative because this requirement is not a sharp, or we can say a little bit. If you do not bundle, okay, just show your judgment why it is okay to you. Or you can bundle these two. There's some space here. Then it will have huge space. Anything else? Okay. So we are finalizing our design here. We decided to bundle here. Then show everything clearly. This is 33 inch. Here to here is 30.5 inch. This is 2 number 4. This is number 3. And here to here is 2.5. Again, make sure who will read this design. Mostly the field engineer, site engineer, or even the labor. So this sketch should be very neat and clean, big, and every dimension should have a cross sec. Cross sec means you wrote here 33, it is 30.5, I wrote here 2.5. So these two, if I sum up, it becomes 33. So good. Now, so mostly we covered everything, tie bar, spacing, this, everything. As we bundle together, we should let the design site engineer know the exact spacing. Now, as we bundle this together, my spacing change. I will have to calculate it. Calculate and tell this way. What is this distance? What is this distance? And from here to here, this distance. Now, which dimension to provide, whatever is needed to place the bar inside, so that when the labor will place the reinforcement, they know where to place it. So to calculate this distance, how to calculate? Not so difficult. Okay, first, maybe what we will do, we will place this two reinforcement at the center. Okay, how much space I have? 16 to 2.5, 2.5, 2.5. From here to here, one bar here, half bar here, half bar here. Here to here, half, half, two. So one bar here, one bar here. So 2 bar 9.8, 2 bar 9.8. That means then I am getting here to here, this spacing. How much space do I have? 16 minus 2, 2.5 minus 2, 9/8. I have 8.75 inch here. Inside the 8.75, I will place 2 bar. That means one space here, other space here, other space here. So if I divide it by 3, divided by 3, 2.92 inch. So 2.92, 2.92, 2.92. So in this way, you will have to provide the exact location of the bar, so that the field engineer or the labor or the site supervisor or the foreman, whoever reads this, he can understand very clearly. So anything else in this beam? So I covered a full beam. In next video, I will try to solve another beam.